Hi, this is Shankar. We will be discussing a uh, topic in waves today, and that is a little bit related to advanced JEE advanced rather than JEE mains, and it is about the boundary transmission of waves from let's say a denser medium to a rarer medium. So we'll have to do a derivation. Okay, before we start though, I want you guys to look at the simulation first. Uh, this is basically a simulation for a wave pulse reflection with both free and fixed end. So let's say you have a wire and that wire has different mass per unit length on one side and a different value of mass per unit length on the other side, which means the velocity of the waves will be different on both sides. And wave optics equivalent of this will be if a wave would be traveling from a rarer medium to a denser medium, or from a denser to rarer, same kind of thing happens but for light. So I want to show you, let me run this simulation. So what is happening here, let's first start with a free end reflection refraction. So the wave that is going, we call it incident ray. The one that comes back is the reflected ray, and the dotted ray that is going forward is known as the transmitted ray. Okay. So in free end, what happen is when the reflected ray comes back, there is no phase difference. But the moment I change this to a fixed end, what would end up happening is when it returns back, it also has a phase difference of 180 degrees when it returns back. Now, there are two things that you have to look for in this. Okay, so two mathematical things that you have to note here. The first thing is that point of the point where the transition is happening, you get a reflected ray and a refracted ray. That point uh, where the interface is there, the net displacement is zero, right? Don't be worried, like some people will get confused here in the sense key, sir, look at this, the transmitted wave and the reflected wave are not actually making zero. But I'm talking about once the transmission fully separates from the reflected ray, you will notice that the point's displacement at the interface is zero. This is something that we are going to use in the derivation. And the next thing I want you to notice is the slope at this location. We will notice this is a very continuous sort of graph. If we assume that there is no power loss during the transmission process, one thing that you'll have to say is the slope of the reflected ray and the slope of the refracted ray both will be same. They will basically be same whether it's a free end or a fixed end. For relative ease of discussion, we will take everything for the free end, because adding up another pi in another phase constant in the trigonometric function will make it a little bit difficult to analyze, but it is still possible. It just will require a little bit more math, but we'll take up the easy case, and that same result that we get for the free end will also hold true for fixed end. So let us start our derivation. Let's talk about a few properties during the reflection and refraction process. Other words for reflection is like the other word for refraction in this case would be transmission. So I want to talk about a few properties, whether they change or not during reflection and transmission. Like for example, velocity. Velocity, there is no change during reflection, but there is change during the transmission process. So once it goes to a different medium, the velocity does change. Now if I talk about other things like time and anything that is related to time, like frequency or angular frequency, they don't change. There is no change in reflection or refraction, right? If I talk about wavelength and something related to wavelength like angular wave number, then there is no change of that during reflection, but there is change when there is a refraction. If I talk about let's say the amplitude and intensity, both of them change. Both of them change during reflection and refraction. Something like phi is the phase constant. So after the during the reflection process, there is a phase change uh, during a certain scenario. So it will not change, it will be zero if you have a free-ended reflection, or if it's going from denser to rarer medium. But if it's going from rarer to denser, or if you have a fixed boundary, then you have 180 degrees of phase change. Refraction may there is no change, so whatever, so you can call the phase constant is basically zero. So during the transmission of a wave during for a fixed or a free boundary, You have to remember these things. During reflection, only the amplitude changes, nothing else changes. For refraction though, except for frequency and time, the transmitted wave will basically have all of them things will change except for time and frequency. So we're going to use that. So what we will do is, first we will start with a discussion on, let's say I have a string which has different mass per unit length, and but the tension is basically constant. So if I fix it on both sides like this, I'll make sure that the tension on the rod, or basically the combination of these two strings, is constant. Okay. However, the velocity is a function of tension and mass per unit length. So if I take the mass per unit length here as mu1 and this one as mu2, then the velocity for the wave on the first part of the wave would actually be under root of t by mu1 and mu1, and the for the second part it will be t by mu2. So that means the velocity will be different. Now what we need to do is, as we understand the wave velocities will be different, I'll have to write some equations to represent them. So the incident wave, I'm going to write it like this: a into x minus v1t. So let's say this is the incident wave that we got. So the reflected wave would look something like b into x plus v1t. So you will notice here that only the direction has changed, so I have replaced minus with plus, but the velocity of the wave remains same. Now if I talk about transmitted wave, the one that goes through to the next medium, so let's say the wave is incoming like this, and some part of it went back, that is the reflected ray and reflected wave, and this one is the transmitted wave, that second part which moves, the dotted line that you saw in the simulation that move forward. Let's say its amplitude is c, and this time I'll have to use a different velocity, x minus v2 into t. So these represent all the waves that we have to talk about. The wave on the left hand side will be a superimposition of two. So the wave, the incoming wave after superimposition will look something like this: a times x minus v1t, and then I'll have to add plus b times of x minus x plus v1 into t. So this is the incoming wave and this is the transmitted wave. So let us apply the two conditions that we talked about in the simulation. The first condition that we are going to apply is the fact that the net displacement at x equals to L. So let me write this down. At x equals to L, the net displacement is equals to 0. So that means the incoming wave should be equals to the transmitted wave. Okay, so this is something that we need to do, okay, mathematically speaking. So a times x, instead of x I'm going to replace it with L, right? So look at this equation. This equation says a x minus v1t and b of x plus v1t. So I'm going to replace this with L minus v1t, and then I'm going to add b of L plus v1t. Okay, and this I'm going to equate it to c multiplied by L minus v2 into t. So this is going to serve as my first equation that I'm going to use. And the second condition that we are going to apply, and this is what we talked about in the simulation. We said that the slope, okay, now how do you find out slope of a wave? You differentiate the wave with partially differentiated with respect to x. So differentiation of the incoming wave, which is a of x minus v1t, and then plus b of x plus v1t at x equals to L should be equals to the partial differentiation of the other wave, like this wave right here. Okay, but just replace it with x. So c something c x minus v2t. Okay, so if I differentiate this, you will notice that this term right here is we're doing partial differentiation, so time we will take as constant. So if you do that, this equation will simply become a plus b equals to c, because all that v1t and v2t, all of that things will cancel. So I get two equations that I can use to find out a relationship between a and c or a and b. Okay, so what we are going to do next is use these two equations, and first we'll try to eliminate b. So how do we do that? Well, we'll find out the value of b from the second equation. We're going to plug it into the first equation. So let me do that for you guys. So what we're going to do here is a into L minus v1t plus, and in place of b I'm going to write c minus a into L plus v1t, and then this is equals to c times of L minus v1t. Now if I rearrange the terms here, I'll get a into minus 2v1t is equals to c of minus v1 minus v2 into t. You can calculate this yourself, like do all the steps properly when you're doing this on your own. This will give me that c is equals to 2 times of v1 divided by v1 plus v2 into a. Now this is a very important relationship and we'll talk about it a little bit later, but this is my result number one. Second result is when we do the same thing, but we try to eliminate c from the previous equation. So what I will do is I'll find the value of c from this equation, which is a plus b, and I'm going to plug that value into the first equation one more time. So the equation would look like a of L minus v1t plus b of L plus v1t, but this is equals to c times of c is this time a plus b into L minus v2t. Okay, sorry, I made a small mistake here. This is actually v2. Okay, and if I rearrange the terms here again, what I will end up getting is b is equals to a into v1 minus v2 divided by v1 plus v2. Now this gives me the two results that I was hoping to get from the beginning of the derivation, which is that if you have a transmission of wave from one string to other with different mass per unit lengths, right, and assuming there is no power loss. Okay, so this is an important result, so I'm just gonna write this down. Assuming there is no power loss, then two important results that you have to remember is that if you want to find out the reflected wave amplitude, then you have to write the incoming wave amplitude into v1 minus v2 divided by v1 plus v2. Obviously you can get v1 and v2 values from doing under root of tension and dividing it with mass per unit length. Similarly you can get v2 also, and the transmitted wave amplitude comes out to be a into 2v2 divided by v1 plus v2. So there you go. I hope to see you guys again.